My name is Taeun Kim, and I'm here to present DAFL, Directed Gray Box Fuzzing Guided by Data Dependency. So let me start with some backgrounds. Fuzzing is testing a program with randomly generated inputs. If we visualize a program as a tree on the screen here, the goal of fuzzing would be to explore every branch that exists in this tree. It has shown successful achievements over time, such as AFL and Google's OSS Fuzz project. On the other hand, we have directed fuzzing, which is a special type of fuzzing that aims to reach the given target locations. This is especially useful when we are generating crashing inputs from bug reports, such as static analysis alarms. Here's some basic mechanism of directed gray box fuzzing. First, we are given a seed pool in a target program. We select a seed from the seed pool and generate mutants from it by mutating the seed. We execute each mutant against the target program, and after each execution, we examine the coverage feedback to decide whether it has achieved new coverage or not. If it has, it is added to the seed pool for later use. Now, since this is a directed gray box fuzzing, every time a seed is selected, we ask the question, what is the distance of the seed? And by distance, we mean how close is the seed's execution to the target location. And as the distance is closer, smaller, we generate more mutants from it in the hope of reaching the target location through that seed. However, there are some limitations in directed gray box fuzzing. First, a noisy seed distance based on control flow graph. This can happen when complex control structures, such as loops, introduce noise in the seed distance. Let's dive into a real-world example to see how this really happens. Here's in CFG, a control flow graph we have extracted from the real-world program SWF2PHP. Since we are to calculate the distance score, each of the nodes are assigned a distance score, starting from 0 at the crashing location. For example, the node over here is assigned a score of 34 because starting from 0, the distance is accumulated over the path. Likewise, another node here is assigned a score of 45 because the distance score is additionally accumulated inside the path in the loop. Now, AFLGo, a previous directed gray box fuzzer, calculates the distance based on all the nodes in the CFG. So given a seed A, when seed A is executed, it first opens a file. It fails at the first sanitization. AFLGo assigns the average of the scores of the node a seed has covered. So in this case, seed A is assigned the distance of average of 34 and 35. On the other hand, we have seed B over here, which opens a file, passes the first sanitization, continues until it fails at the second sanitization. Since seed B passes the first sanitization and also covers the nodes that are closer to the target, this is intuitively a better seed, and we should prioritize this seed. However, AFLGo assigns a distance score higher than the previous seed, and as a result, AFLGo prioritizes seed A over seed B, which is a counterintuitive decision. WindRanger, another directed gray box fuzzer, tries to enhance this mechanism by focusing only on the diverging nodes. The diverging node for seed A is the first sanitization node because that is the node that prevents seed A from reaching the target location. So seed A is assigned a score of 34. Now, the diverging node for seed B is the second sanitization because that's the node that prevents seed B from reaching the target location. So seed B is assigned a score 45. Now we can see that WindRanger will still prioritize seed A over seed B, so the problem isn't really solved here. DAFL's solution is to utilize definition use graph, in short DUG, to calculate semantic relevance score. In order to obtain the def use graph, DAFL first performs data dependency analysis on the program, starting from the crashing location. Since the crashing node here uses f and type, we track down all the program locations that participate in defining the value of f and type. And with this information, we can draw the DUG as shown in the screen. DAFL also assigns scores to each of the nodes, but this time it's not the distance score, it's the semantic relevance score. So the nodes that are furthest away from the crashing location is assigned the lowest score, and as it gets closer, it is assigned a higher score. And eventually, the crashing location, the crashing node, is assigned the highest score among all the nodes in the graph. Now, given seed A covers a single node in the DUG, which is assigned a score of 1. And it is directly assigned the score of 1. On the other hand, we have seed B, which covers 2 nodes in the DUG, each assigned a score of 1. And DAFL assigns the sum of all the scores of the nodes that it has covered. So seed B is assigned a score of 2. And since this is a semantic relevance score, the higher is the better. So DAFL can finally prioritize seed B over seed A, solving the problem. Here's the second limitation, the negative coverage feedback, which can happen when the fuzzer generates seeds that cover irrelevant program locations. Let's revisit the previous example, but this time let's look at the call graph, starting from the main function. The main function calls 4 different functions, and one of them, the function block parse, can call the function that eventually reaches the target location. However, the pitfall here is that block parse can call 80 other different functions that are irrelevant to the target location. Let me show you how this can impact our seed pool. Given our seed pool here, let's say that we have successfully generated a promising seed that has the potential to reach the target location. And since we are to favor this seed, we have generated 5 times more seeds than usual. However, many more seeds can be generated from these 80 other irrelevant functions, and as a result, our promising seed is easily outnumbered in our seed pool. DAFL's solution is to selectively receive coverage feedback by selective coverage instrumentation. Since DAFL performs data dependency analysis, it can successfully identify the functions that are relevant to the target location. And DAFL focuses on these functions by only instrumenting these functions to receive coverage feedback only from these functions. And as a result, no seeds are generated from the irrelevant functions, and our seed pool can be focused on the promising seeds. So these are the key concepts of DAFL, and now let me give you an overview of DAFL. We are given a program with a target location. Then we enter the static analysis phase, where we run the static analyzer to obtain diffuse graph and the list of relevant functions. Then we perform selective coverage instrumentation, where we utilize the list of relevant functions. After instrumentation, we enter the fuzzing phase, where we execute the instrumented program. After each execution, the selective coverage feedback is generated, and with the joint use of diffuse graph, we calculate the semantic relevance score. With the calculated score, we perform seed scheduling, where we decide which seed should be chosen first and how many mutants to be generated from the chosen seed. When the mutants are generated, we execute them, and we repeat this process until the target bug is found. With this approach, out of 41 target bugs, we were able to show best performance in 27 cases. We reproduced bugs almost 5 times faster than the state-of-the-art directed gray box fuzzers, and we found 6 more bugs within the given timeout, which was 24 hours. Here are some more details on our evaluation, where we performed a crash reproduction test on the benchmark of 41 CVs from 10 programs, and with the baselines of 1 undirected fuzzer, AFL, and 3 directed gray box fuzzers, AFLGo, WindRanger, and Beacon. Our criteria was the median time of 40 iterations to reproduce the target bug. And here's the results. On the x-axis, we plotted the target CVs, and on the y-axis, we plotted the time to reproduce the target bug in seconds. And note that the y-axis is plotted in log scale. So we have the results of AFL, AFLGo, WindRanger, and finally, the DAFL. Now, it is clear that DAFL clearly outperforms the other fuzzers, and especially when most of the other fuzzers resulted in timeout, DAFL could successfully identify and reproduce the target bugs. Overall, DAFL best performed in 27 cases. It was almost 5 times faster and found 6 more bugs within given timeout. Here's a summary of our presentation. Directed gray box fuzzing has some limitations, which are, first, noisy seed distance, and second, negative coverage feedback. Our solution we present today is DAFL, directed gray box fuzzing guided by data dependency. The key concepts of DAFL are semantic relevance scoring and selective coverage instrumentation. With these two key concepts, we achieved 4.99 times performance boost against the state-of-the-art gray box fuzzers, directed gray box fuzzers. Our work received all 3 of the artifact batches, and this is the link to our artifact, so anyone interested can try it out, because we opened all our experimental environments in Docker, so it'll be easy to reproduce the results. Thank you for listening, and I'll be happy to answer any questions. Thank you.